Good morning, good afternoon, good evening, depending on where you are. Thank you very much for joining us today for the second webinar in the series of webinars on Slide2, which is an exciting slope stability analysis tool from rock science based on limit equilibrium method of slope stability analysis. And in this second part of the webinar today, we are going to discuss the seepage and stability analysis. My name is Manoj Verman, and I represent rock science in South Asia and India included. Sorry for starting a couple of minutes late because I was waiting for more people to join in. As people were joining in, I thought let's wait for a couple of minutes. And so as far as groundwater analysis is concerned, we really need to understand the inflows and outflows which affect the groundwater regime. And you see a lot of these things in the sketch that you have on your screens right now. And water can be present in all sorts of mechanisms, which could be ranging from precipitation, the surface runoff directly into the streams, the rivers and streams, in contamination, the aquifers, for instance, the water present in the discontinuities in the rock mass, the water in the fractures in the bedrock, the pore water which you find in soils, sands, etc. So all sorts of water is present, which has a very important impact on geotechnical engineering. And so today we are going to see how we can incorporate the pore water pressure in slide 2 so that we can carry out the seepage and stability analysis. Now, how the pore water pressure is defined really is, take for instance, this bottom here, and the height of water above this base is HW, because that's the water table surface. And the pore water pressure, because of this, would be height multiplied by the unit weight of water, which is what you see here in this equation. The first equation, U, which is the water pressure or pore water pressure, equal to the groundwater, the unit weight of water multiplied with the height of water, gamma W multiplied by HW. And what you see below this is the concept of effective stress. And I'm sure all of you know about this, that effective stress is equal to the total stress minus the pore water pressure. So effective stress appears in many formulations. And so, for instance, shear strength drops down as the pore water pressure goes up because effective stress comes down. And so, which has a direct impact on the factor of safety. And that's what we are going to look today, the impact of pore water pressure on the factor of safety. In other words, the stability of slopes. And we are going to look at various examples. But before we look at the examples, it is pertinent to share with you that in what are the options in which pore water pressure can be defined or specified in the software slide 2. So there are many options available, and we will try out these options today through examples. For instance, you have an option of water surface. You can apply the pore water pressure in terms of water surface, and we're going to look at a couple of examples for this. One affecting the pore water pressure development in the domain, and the other one not affecting the pore water pressure as such, but adding to the ponded water. And so that particular example is from a real life case study, which is a failure of a levee during Hurricane Katrina in 2006. So water surface is one option. Another option is piezometric grid data, and we are going to look at some examples for that, how to apply the pore water pressure in terms of piezometric grid data. And then you have the pore water pressure ratio, RU method, and finally you have the steady state seepage analysis, which can be carried out in slide 2 using a finite element method engine, which is built in slide 2. So that's going to be an exciting thing to see, and we are going to look at some examples of using these steady state seepage analysis using finite element method within slide 2. And so let's move forward and look at the examples, starting with how to use water surface to define the water, and then carry out the analysis and obtain a factor of safety, and to see whether the slope is stable or not. So we're going to look at two examples here. The first example, which is on the left, is an open pit, and the one on the right side is the levee under flood, which I was just talking about. So let's look at these examples one by one. And before we go to the examples, let's understand a bit more about how to specify the pore water pressure. And in slide 2, and in terms of water surface, which is the phreatic surface. Now, what you see here on your screen is a phreatic surface which is at an angle theta from horizontal, and the equipotential lines are perpendicular to the phreatic line. So that's the height that we need to include in the calculation, the HU and not H. So HU would be equal to H cos squared theta. You can derive that. And so the pore water pressure will be defined like this: gamma W, which is the unit weight of water, multiplied by HU, which is H cos squared theta. And this can be rewritten in the form of gamma W H, capital HU, and the capital HU is a factor which can be defined while you define the material properties in software slide 2. You can see the options here. There are two options: automatic options, auto, or custom option. And HU equal to 1 would indicate hydrostatic conditions. And values of HU between 0 and 1 can be used to simulate the head loss. So any head loss due to seepage would bring the HU down. So in the examples that we are going to see today, we'll keep HU equal to 1, and which means we would be on the conservative side. Okay. So let's look at the first example, which is an open pit and the application of phreatic surface, and to carry out the analysis after that. So this is the example that we are going to analyze and see the factor of safety. And so let's go to slide 2 software. Just allow me a moment to launch that software, or I can directly go to the example. And I think I can go to the example directly. And as you can see here, we have 6 examples today for you. Hopefully I would be able to complete them within the stipulated time. The first example that we are going to see is, as I mentioned, open pit with phreatic surface, application of phreatic surface. And so let's straight away start the program. It's coming on now, the model. And that's the model you see in slide 2 of this problem that we are going to analyze today. And what you see here is the material properties have been included here on the screen. And these are molecular materials in the slope and here, and with the cohesion and friction values mentioned here. Water surface is none. We have not applied any water pressure yet, water surface yet, although we have specified that the form of application of water would be in the form of water surface. And you do that when you go to the project setting and go to groundwater, and you see that's what we have seen, water surface. We look at other options in the more examples that are coming up today for you. And the method that we're going to use for this analysis, out of the several methods available, we'll use only one so that the analysis is done faster. Of course, you can choose one or many other methods and compare the factor of safety. So we'll use Spencer just for an example. I'm not going to change anything, so I'll cancel this. And so let's run this analysis without any water surface. As you can see, there's no water surface applied as such for now. So let's run the analysis and see the results. And here is the result. And you can see the factor of safety is 1.578. Usually for these slopes, you would be happy with a factor of safety of 1.5. So this is a stable slope. But remember, we haven't applied any water yet. And let's see what water can do to this, the factor of safety and the stability conditions. And so let's go back to the modeler so that we can apply some water, which is here. We can go back to the modeler. The modeler opens again. And what we can do, we can create another scenario. We can just copy this scenario, add scenario, and we can rename this scenario to indicate that we are going to apply phreatic surface. Phreatic surface, the name, we give it to this scenario, save and close. So now you can see that we are going to apply the phreatic surface to this. And for that, let's import the phreatic surface, which is already with us from DXF file. So go to File, Import, import DXF, and we go to the examples folder and go to this open pit and phreatic surface, and that's the DXF file waiting for us to be picked up. And there it is. And it's just a line, but water table has been assigned to it. So when we say OK, this would be applied to a model. And before it does that, it asks that which of the material the water table has to be assigned to. So we choose select all the materials have been, the water table has to be assigned to all the materials which are present in that model. So you can see the water table has been applied, and you can immediately see that table has been updated, and you have the water surface now. And HU is 1, so as I said in the beginning, we are on the conservative side. And so let's run this analysis now. So I need to save it somewhere first so that I can then compute. Just give me a moment. And I can save it here and then do the computation. We can, the first one we have already done, so we only have to do for this phreatic surface scenario. The computation is in progress. It's done, so we look at the results, go to interpret to see the results. That's the previous one, and the new one is coming up now. So as you can see, the factor of safety has dropped from what you had earlier, which is 1.578 to 1.219. So as I mentioned earlier, if the required factor of safety was 1.5 in this case, then with the presence of water in the form of phreatic surface, the factor of safety is now not acceptable. It is much below 1.5. It has dropped down to 1.219. And so you can also see the development of, let me see if I can tile them together. Does it look like though? Let me try. No, for some reason it's not possible. Anyway, it doesn't matter. So we'll check for the water, the pore water pressure. Flow value along surface, we'll choose the pore pressure here. And you can see the presence of pore water pressure along the slip surface in this case. And so because of which the factor of safety has come down from what you saw earlier as this one, 1.578 to 1.219. So, okay, so let's go back to the presentation. Just give me a moment. And let's go back to the presentation. There we were. Let's go to the next example, which is quite an interesting example, and it's a real case study. Levee and water surface. We are again going to use the water surface in this case, but there's a slight tweak in this. So we are going to see the effect of ponded water load, and we are going to create a tension crack, and we're going to see what is the impact of the ponded water load and the presence of tension crack on the factor of safety. And this actually is the case study which has been heavily investigated. Lots of papers have been written on this. This is from New Orleans, where during the Katrina hurricane in 2006, the levee here failed, and the failure mechanism is explained here, which is a result of lots of investigations which have been done, and finally this was the accepted failure mechanism. The rising water in the canal that you see here, because of the hurricane, pushed laterally against the flood wall. The canal water, which is rising rapidly, pushed against the flood wall, and eventually and progressively opened a gap between the flood wall and the outboard section of the levee embankment. So this gap was opened because of this, pressure and the rising water. And then in the second stage, the water entered the gap which was created, and entered the gap and increased the lateral push against the sheet pile. And as the push continued, the shear failure of the foundation occurred, which you see in the sketch below. So how are we going to simulate this condition in slide 2? And what we will do this, that the water filled gap we'll carry out the modeling of the water filled gap. So by modeling of water filled gap by removing the soil on the loaded side. On this side, we'll remove the soil and apply the hydrostatic water pressure to the wall here. That would simulate the condition which existed there when the water entered and put the lateral pressure on the sheet pile, which actually which failed, the foundation of which failed. So we'll look at this simulation. We will bring it in the model, and so for that, let us okay. So for which we have to go to the example again, and the example is right here, Katrina, and we start the program. So the model is there for you to see the levee and the water. You still can't see the water table as yet. We'll just create that. And so one important thing that you see in the table of the material properties here is that they're all cohesion only material. There's no friction, cohesion only material, which means the pore water pressure through this material will not come into equation. And so it will all be ponded water. No pore water pressure in these materials. And so the line here has been drawn to create the water table. So if I right click on this, you can assign a boundary, and we're going to assign the water table to this. And in this dialog box, since we are not going to apply the water pressure, the pore water pressure to the materials, as I just discussed, we will not apply this to any of these materials. So this would just act as a ponded water, which is what was the case in that levee. So having applied this, let's go and do the analysis. And compute. It's just getting completed. Okay, the computation is done. Let's look at the results. And you can see that the factor of safety is quite acceptable, 1.523. And if the acceptable factor of safety was 1.5, this is okay. Now this is before the water entered the gap and started to push the sheet piles. It's before that. So now we're going to simulate that condition which I was talking about. So factor of safety is okay. That's before the mishap. And so let's go back to the modeler here. And what we're going to do, we're going to create a tension crack here. And we're going to, okay, before I do that, let me enlarge the view so that you see what I'm doing. Let me just put it in. Yes. Okay. So that's the add tension crack option. So we will choose this side of it. And then in a horizontal here, you will just see what I'm trying to do here. I'm trying to apply the tension crack to the model there. And you see these tension cracks here. And so tension crack have been created. We'll put water, we'll create this gap here. So let's assign the property, tension crack property. It's dry at the moment. So we'll put some water in this. using the water table. So now they will all turn blue, which means the water table is now in this gap which we have created. Okay, so let me see if anything else to be done, and otherwise we can just go and run the analysis again. Ready for the analysis computation. Yes, it is completed. Let's look at the results. This is the previous one, and the new one is coming now. As you can see, there's a drastic drop in the factor of safety there, and this would definitely indicate a failure. And because of this low factor of safety, the levee failed. And you know, if you can compare this with what we had earlier, 1.523, and now it is 0.776, much lower than acceptable value. Certainly failure is happening. And let's put and see some you know, let's go to the modeler. No, not the modeler, sorry. Let's look at the slice data, the vertical slices, and let me enlarge this so that we look at these slices, and look at the first slice here. Okay, and the very first slice, and if I click on this, the data would be shown in this table, and you can see there's a lateral thrust being applied on the first slice, which is, if you look at this table, which would be this is the one, left side normal force. So this force that you see here, the lateral thrust which is being applied by the water, is equal to the hydrostatic water pressure, and because of which the entire hydrostatic pressure was being applied onto this the first slice here, and levee failed, which is reflected in the poor factor of safety that you just saw. Okay, so let's go back to the presentation now. Let me just close these. And we go back to the presentation. So that's where we were. Let's move forward from here. And after those two examples, let's go to the finite element seepage analysis, which is included in slide 2. And what you have here is, sorry, just a moment. Yes, in this section, we're going to look at 3 examples. One is of an open pit, one of an embankment, and one of a levee. We'll start with the example of levee, which is on the extreme right, followed by the one on embankment, and then the open pit on the left, the third one. So before we go and look at the examples, let's understand that the difference between steady state and transient flow. And steady state flow assumes that there's infinite time available for pore pressure to equilibrate to the applied stresses. Okay, and groundwater inflow is equal to the groundwater outflow, and therefore there is no change in the storage in the domain which you are analyzing. So whatever comes out goes out, whatever comes in goes out. And this should, however, be confirmed by studying site monitoring data to make sure that it is really a steady state situation. Examples of steady state: long-term post-closure condition in pit slopes. You know, the pit, open pit mine slopes which are closed down after production is over. The long-term post-closure conditions would be kind of steady state flow conditions. Another example is the materials which are highly permeable, they would they would have a situation that equilibration of pore pressure occurs very quickly, and also situations where the change in pore water pressure occurs extremely slowly, so that transient effect can be ignored. It's just the opposite, very, very slow change in pore water pressure, so that you can neglect the transient effect. And those are the examples of steady flow. And as far as transient flow is concerned, sorry, let's go on ahead. Transient flow is concerned. Transient flow is the response of the system to changing hydraulic stresses. So it's over time. And examples of transient flow are excavation of the pit, lowering of water table or water levels due to mine dewatering, etc. That's another example. Impoundment of dams or drawdown in dams, which is a transient flow situation. Flooding, rainfalls, all of those are the transient flow examples. And how do we specify the pore water pressure in these situations? Now, take for example point A here, which is located below this water table, and the total head is H, which is measured from a datum from which everything is measured here, and the pressure head is psi. So the water pressure at point A would be psi, which is the height above point A of water multiplied by the unit weight of water. Now, when we carry out numerical modeling, as you would know, we have to specify the boundary conditions. And since we are going to use the engine which is built in slide 2 for carrying out the numerical modeling analysis using finite element steady state seepage analysis, we have to specify boundary conditions, and the options are here, which you will see. Plenty of options available. You can apply the boundary conditions in the form of total head, or pressure head, or pore pressure, nodal flow, which is kind of the pumping in and out of water, infiltration or recharge from precipitation, the rainfall, and seepage phase. I'll explain seepage phase. And transient boundary condition includes all of these, what is listed now, but any time dependent tabular function of these conditions. You will see the examples a little later. Now, the examples of boundary conditions are two examples shown here: constant head and seepage phase. Constant head, if you look at this sketch here, where the cursor is, as it is mentioned here, A, B, C, and E, F, G. A, B, C, and E, F, G. These segments are the example of constant head, where you have presence of water at all times. Constant head of water is present at all times. Those are the constant head conditions, and which can be specified. We will specify. Let's see a little bit more about this. Here is an example of swampy area here, swampy area, and this could as well be a river with a constant head, and that's a constant head situation. Now, if you dig a pit next to it, dewatering pit next to it, and you're not doing excessive dewatering, as long as whatever action you're taking is not affecting the head of water in the swampy area or the river, this would still be the constant head situation. But if you continue to do dewatering to such an extent that the swampy area dries up or the river dries up, then it is no longer a constant head. So which means the constant head situation is one where you have inexhaustible supply of water, where the water supply is never exhausted. So that is where you give the boundary condition as constant head. Okay. Seepage phase, the other boundary condition. Now this simply means, seepage phase simply means that the total head, which is H, you can see H here, total head, must never exceed elevation head, H. Now in this figure you can see H is much larger than Z, but that's not the seepage phase condition. Seepage phase condition is when H can never exceed Z, or in other words, to fulfill this condition, which means that H is never less than Z, psi has to be equal to or less than 0. Psi has to be equal to or less than 0, which means a seepage phase condition to occur, the maximum pore pressure is limited to 0 or there is no water standing on top of this node. That's a seepage phase. No water standing on top of this node. We look at the physical meaning of this, and that explains the physical meaning of it. A saturated zone that intersects the ground surface at atmospheric pressure. The water discharges because of evaporation at that, or due to downhill film of the flow. Let's look at this example here. Right here, you have this trench here which is filled with water, and you have this water here, but nothing stays on these surfaces here. So these surfaces here and here, they are the seepage phase. There's no water on these surfaces, which means the water is always below zero or zero at that locations. So those are the seepage phase conditions, and we'll see how we apply this in solving some problems. And the general location of surface is known, of these surfaces is known, but the length of these surfaces is unknown prior to numerical analysis. But after carrying out the numerical analysis, you would know the lengths of these surfaces which are assigned the seepage phase condition, boundary condition. Now we're going to look at this example, which is levee and relief wells, and so we're going to see through this example the effect of relief wells on the factor of safety. First, we'll carry out without the relief well, and then we'll see if the factor of safety is low, how we can improve the factor of safety by adding some relief wells. And I'll explain what relief well is at that stage. So let me just go to the examples of relief well, which is here, levee and relief wells, and we're starting the program. So what you see here is that this is the condition here. You have the retaining wall here, and the levee, the yellow material, that is the levee, and the water surface is 115 feet here, and you can see that here. Okay, let's carry out the finite element analysis, for which we have to specify certain things. Groundwater, the method would be steady state finite element analysis. Okay. So as soon as we choose that option, another tab opens here for steady state groundwater. This is for slope stability, and this is for steady state groundwater. And as you would know, in finite element analysis, we have to create a mesh, divide the area of interest in mesh. Let me just. And so in rock science software like Slide2, as far as finite element is concerned, or RS2 and other ones, there's a one-click mesh generation available, which is this one. And I'll use this. And you see the mesh has been generated. Now, we are more interested in knowing the values and the calculations in the vicinity of the levee. So I will sort of use more dense mesh in that area by using this option here, increase density through a window input. That's the window I chose. And you can see the mesh has become dense here. So more calculations will be carried out. We'll get more accurate information about the things like pore water pressure, etc. in areas close to our area of interest. Okay, so this has been done, and we have to apply the boundary condition. As we know, the water level is 115 feet here, so we need to specify the boundary condition here. It's getting stuck. And so we pick up the set boundary condition option, and we apply the total head, because total head is 115 here, and we'll give that value here, 115, and we apply it to this, and we can just make it a little small so that we can use the window option to apply on this surface. This is, and we can assign, I think, So yes, it has been assigned. 115 feet of total head has been assigned, as you can see here. The boundary conditions have been assigned. So I think we are ready to carry out the analysis, for which let me just save it once again. And we can do the compute then. Oh, I think I should have done the slope. Let me do it again, because I should have selected the slope stability, because then it will compute for slope stability as well as the steady state groundwater. Okay, so the first one you just saw was for the groundwater, and this one is for slope stability, which is happening now. It's done. We can look at the results. And there you can see the factor of safety, which is 1.167. As you would imagine that usually one would expect the required factor of safety in these cases to be 1.5. So this is definitely a lower factor of safety and than what one would imagine. And so we need to do something about this. So if we go back to the modeler, and we had already created this line here, we can try to use the option of relief well in the steady state groundwater condition. And for that, let us create another scenario. So we will add a scenario here and give it some name. Relief wells, or well, it doesn't matter. So in this, if you choose this, line has already been created. What a relief well is actually, when you provide a relief well, it has the same total head as the head of water at the top. So at the top, the water head is 106.49 feet. So we can apply the same here. So we can choose this and set total head. It's asking for the total here at the right bottom, and 106.49. So that value has been given there, and you can see those values mentioned there. So with this relief well, let's carry out the analysis once again, and let me just check. It's okay. Yes. Compute. We only need to compute for the relief well option. Previous one we have already computed. That's the groundwater. And now the slope stability. Yes, that's slope stability. It's done. Let's look at the results. That's the previous one. 1.167 was the factor of safety without relief wells, and with relief wells, the factor of safety improves to 1.521. And no, we don't. Okay, 1.521. So this is an acceptable factor of safety. So the provision of relief well has improved the factor of safety. If you can compare what was earlier 1.167 and now it is 1.521. And if you look at the pore water pressure values along this slip surface, you can choose pore pressure, and you can see that the pore pressure is 397. Let's compare this with what was the pore pressure earlier. and we'll apply the same thing will on this pore pressure, and see it was 611. So if you compare from 611, it has dropped down to 397, and because the relief well. Another thing, if you notice, the water surface has come down. So in this, the previous case, that is the water surface here, and now it has dropped down because of relief well, and because of which the factor of safety is improved, and the pore water pressure is reduced from 611 to 397. So that is the advantage of using relief wells, and so that's how you see. So you have seen two examples here, and let's go to the presentation. Back to the presentation. Let me close these. Files, and so we go back to the presentation, which is here. So we've looked at the effect of relief wells on the factor of safety. Now let's look at the next example using the finite element analysis, and which is the impact of the drainage system on the factor of safety. Okay, and for which we are going to take this example of an open pit. On here you have the constant head here, this side of the open pit, and this side of the open pit is the dry area, where the working area in the pit, and this side the water is there, the constant head. And so let's go to the examples again. And we go to this example, drainage system in an open pit, and we start the program. So you see the pit here, and you see the steady state groundwater tab here, which shows that there's a constant head of water here because of presence of reservoir or something here. And here it is a seepage phase chosen here, which means the water is not there. Any water present will be removed from there, so that the working area is provided for the open pit mine on this side. So we can carry out the analysis and to see what sort of factor of safety we see here. And so let's look at the results. And that's what we see, 0.976, which is a low factor of safety. It's not a stable slope. So we need to do something about it. Okay. Okay, so let's go back to the modeler. And what we can do here is that these lines have already been provided. What we are going to do with these lines is that we are going to provide drains. We are going to use them as drains, and we are going to provide some drainage so that the pore water pressure can be dissipated. And but before, okay, so we'll create the seepage phase here and seepage phase here. Okay, and we can run the analysis. Let's see the improvement, the results, if at all anything is there. Okay, compute. I should have created a scenario, so that it's always good to create a scenario, which I should do now, or should I carry out like this? Okay, I should have created a scenario, which I did not. So anyway, we'll carry out this analysis as it is. Just a minute. Let me just carry out analysis again. There was an issue here. This is taking a longer time because we are doing it live, and since most of us are working from our homes, we are using our laptops for carrying out the analysis, and so it's taking a little longer time. It's done. Oh no, the groundwater part is done. It's going to be over soon. And it's done, so you can look at the factor of safety obtained. This was the previous one, 0.976. And now, with the drains provided, the factor of safety improves to 1.248. So if in this open pit mine, the required factor of safety was 1.2, the slope is safe now. Earlier it was not safe, and you can compare with this one. The 0.976 was the earlier one, and now it is 0.248. Another thing that you see here, if you compare this with this, in the previous one, you see this is how the water table was going, almost touching the surface. But now it has been pushed back. The magenta color, the purple color, it has been pushed back because of these drains. It's been pushed back, and I'm not sure if we can or we should do this because we are running out of time. Okay, you can see some pore water pressure. It's okay. So that way you can see the influence of providing drains and using a finite element analysis in this. So let's go back to the presentation. So we have seen the effect of providing the drainage system on the factor of safety. And it's a crucial thing actually in open pit mine in this case, but also civil engineering slope instability programs. One of the several methods available to you for improving the factor of safety is, in addition to providing the support measures, is the drainage condition. And depending on how big a role the water is playing in you making your slope unstable, sometimes drains can be very effective. Usually drains are effective because water has a very important role to play in lowering your factor of safety, and drains would be very useful. The advantage is that you can actually, based on the site conditions and what you think is implementable, you can carry out schematic arrangements of the drains to be provided, and then try to simulate that arrangement through modeling like these, the length and the angle, etc. of the drainage system that you plan to provide, and you can see the improvement in the factor of safety. So you can take a decision based on what works best for you. Often it could also be a combination of at what angle you want to cut your benches and the overall slope vis-a-vis the cost of drainage, etc. So all those decisions can be taken once you carry out these analysis. So it's a very important tool to have for any of such decisions to be made. Okay, now let's look at another example, which is transient drawdown. It's a pretty common problem. Let's look at transient drawdown situation. And what we are going to do here is we are going to see this embankment where you have this drawdown happening from 20 meters to 40 meters in 6 days, linear variation. Okay, so let's go to the example straight away. It's transient drawdown. And what you see here is that, if you go to project setting, you see, the groundwater steady state finite element analysis has been chosen. An advanced option has been chosen because so that you can give if you don't choose advanced, you can't choose this transient groundwater. So advanced, and under that transient groundwater option has been chosen for this. And if you go to the transient tab, you see the stages have been specified here, 5 stages in terms of time, and the analysis would be run in that sense. So let me just cancel this. And what you see here, you have 3 tabs here: slope stability, which is what you see, and steady state groundwater. In the steady state groundwater, and then we'll go to the transient groundwater. In the steady state model, you see that that's the water on this side, and these green lines are the discharge sections that we have created so that we can capture the value of the water passing through these discharge sections. So we can look at how the water is moving through the body of the embankment, and then to transient groundwater, you have this boundary condition here in red, which is the transient boundary condition, and this is if I click here, you see the set transient boundary condition. Gradual drawdown is the option chosen, and if I click on edit, you can see what all is there in this condition which has been specified. You have these stages here in terms of time, initial stage 2 days, 4 days, 6 days, and the drawdown taking place as like this: 20 meters, 18 meters, 16 and 14 meters, following this straight line relationship. So the analysis would take this into account, and we'll see the results of these things. Okay, so that's it. So we can see the results here. And so you see the factor of safety of 2.24 in the initial condition. And then we go to the 2 days, 4 days, etc. as the drawdown is happening. So you see in the initial stages, without any drawdown, the discharge of water through the embankment is pretty constant. It's 1.32, 1.32, 1.32 through these discharge sections. And the factor of safety is pretty good, 2.214. Let's go to the next stage here. You look at the tabs here. Stage 1, which is 2 days. After 2 days, some drawdown takes place, and transient conditions are there now. As you can see, those red things. And you immediately notice that the discharge is not constant, which is what you would expect in the case of a drawdown, which creates the transient water flow conditions. And in fact, some water is actually going out of the embankment here. And the factor of safety drops to 1.828. 4 days, when the more drawdown happens, the factor of safety drops further, 1.41. The water is not constant. Some more water starts to go out of the body of the embankment here. If you go to stage 3, which is 6 days of drawdown, the factor of safety is now critical, because this is a critical stage where the factor of safety falls below 1, so unsafe conditions. Okay, so and water is going out of the embankment here, so pretty unsafe conditions here. And if you look at the flow vector, if I click here, you see how the water is actually going downstream and upstream from the body of the embankment. You can see through these flow vectors. And if we see the the pore water pressure distribution on the slip surface, pore pressure, it's imbalanced pore pressure in downstream and upstream side, and high pressure building up, because of which the shear strength is reducing and the factor of safety is going down. So during the drawdown, this kind of analysis tells you which is going to be the critical time or critical stage of the drawdown where the slope might fail under dropping factor of safety. So that's what you can see here in this transient condition. And so we have to complete this in the interest of time. I won't be able to spend much time on this. You can see, just for the academic purpose, the rest of the conditions, the factor of safety dropping further. Okay, so we'll go back to the presentation. Let me close this. And we're back to presentation for the last example. It's quite an involved example, and we are going to apply the water pressure in terms of piezometric data on a grid pattern. And the example that we have here for you, the last one, is a tailing dam in a mining situation, tailing dam, and on top of which an embankment is to be built. Okay, so as you would imagine, when you build an embankment, there's always an issue of excess pore water pressure and how fast or how slowly that excess water pressure has to be dissipated. And based on that, construction sequence or the time to be taken in construction of the embankment is to be decided. Construction stage pore water pressure situation. So construction of a new embankment in a tailing dam or on a tailing dam. So that's what we are going to see. Now, for this kind of a situation, you have to have some special kind of formulation involving hydromechanical coupling. Beg your pardon. Hydromechanical coupling as to find out or determine the excess pore water pressure in tailings due to construction of a new embankment. And for that, you have to carry out a consolidation analysis. And for which, what we will do, we'll quickly go to another software from Rock Science, which is RS2, finite element based general purpose program. And that's what you see here, an RS2 model here, in which we'll choose the consolidation option, coupled bio, and we'll carry out the consolidation analysis. And we'll choose an advanced material model, which is Norsen, which captures the static liquefaction, which the more Coulomb material is not that effective in doing. So, through this analysis, we will see the initial pore water pressure and the excess pore water pressure. These contours of initial pore water pressure and excess pore water will be seen by us. And on the basis of that, we'll see how a rapid construction or a slow construction will affect the factor safety. Okay, so let's go to that example straight away, and which is here, the tailing dam. And I will show you the RS2 thing first, which is already there actually. This is the RS2 model, and in which you will see that if I go to project setting, you will see that under general, you have this consolidation option chosen as coupled bio. That's what I was trying to tell you. And if you go to stages, you have two stages specified here in this model: initial stage and then the second stage during which the embankment will be built, the second stage. And these two stages are seen at the bottom of this here. Initial stage is what you see now. If I click on this second stage, you see this the yellow material, the embankment has been built. So once again, initial stage where the embankment has not yet come, and the second stage where the embankment has come. So if you see the results of this RS2 analysis, you will see this, the pore pressure distribution in the domain in the initial stage and after this embankment is built. So if I compare the two, this with this, you can see that the excess pore water pressure developing because of building up of this embankment. So what we'll do, we will use the results of this analysis to carry out the further analysis in slide 2. So we'll export these values of pore pressure, which have been carried out as the result of the consolidation analysis, like this: file, export, and export values at all nodes. We'll export, and this would be saved as an Excel file, which has already been done, so I'm not going to do it now. I'll show you the Excel file a little later. So the results of this analysis are all shown here in the form of saved pictures, and this is the initial condition of the pore water pressure that you see. And here in the next picture, what you see here is that the excess pore water pressure, considering that you are carrying out the material is elastoplastic, the typical Moore Coulomb material, and if you carry out an analysis like that, the pore water pressure is 170. But if we replace this with loose sand and choose the advanced material model, just for a moment, let me go back to RS2, where I would like to show you the properties of the material. And before I do that, you see the Norsen tailing material is represented by a Norsen advanced material model, which is found here. Properties, define material, and you see if you go to tailing Norsen, go to strength, that's the advanced material model. As I mentioned some time back, this is a material which captures the static liquefaction. Okay, so the right selection of material model is so important in certain cases. So let's go back to those pictures that we are having a look at. If you carry out an elastic analysis, this is what you see. The excess pore water pressure is 170 MPa maximum. But if you replace this with loose sand and the Norsen advanced material model, this is actually 600 kPa excess pore water pressure. So you can see the difference between choosing the right material model and an incorrect material model. And so this is the value that you would expect: 600 kPa maximum excess pore water pressure by building this embankment at 20 days. So at 7 days, 7 days. And if we take some more time in building the embankment, let's look at the next option, which is 10 days. As expected, the excess pore water pressure is a little less now. And if you take a little longer time than that, say 20 days, you can see at the top here, left top, 20 days, then the excess pore water pressure drops further to maximum value being 520. And if you take a month, 30 days to build this embankment, the excess pore water pressure drops further to 490. So that's how you can decide about this. Now, we are looking at the excess pore water pressure values, but let's look at the factor of safety also, and for which we go to the slide model and go to the example and go to slide model, in which we'll import the results of the analysis of consolidation done through RS2. And what you see here is that in the steady state, the master scenario is these are the pore water pressure indicated through this. We can turn it off so that you can see it clearly. Where is that option? Here, water pressure gate can be turned off, and in the 20 days you have this kind of a situation. Okay, and what we're going to do, we're going to import the values that we said, but before that we have to see how we apply. Okay, let's first carry out the results. First, let's see the results. And the factor of safety, you can see 2.038, initial condition. Okay. Okay, yes. Now let's apply the piezometric grid to the modeler, and that's what we're going to do. Project setting, groundwater, and grid of pore pressure. And what we're going to do is, that's the thing opens, and we go to the values that we saved from the RS2 analysis, which are saved in the form of an Excel sheet here. And that's what it is. So we'll copy this data and copy this and take it to the slide model here and paste. So that data is now here. XY coordinates and the pore pressure, which were generated through consolidation analysis in RS2. So OK and OK. And now you see there is this here. So we can turn off the water grid here. Now, if we look at the initial condition, and this is after embankment, if you look at the property view here, open property view, This is what you see in terms of pore pressure contours in the case of embankment. And as far as initial conditions concerned, if you look at the property view here, viewer here, this is what you see. And if you tile them together, and let me lock the zoom and enlarge it, shift it so that you can see. So you can see the influence of the building of this. This is the initial condition on the left, and what you have here is the embankment, 20 days, and this is, you can see the higher pore water pressure created here because of embankment. Okay, so let's close this. And run the analysis. Okay, so this is done. We can look at the results. So that's the result, that the factor of safety is 0.946, which is a low factor of safety in this case when we build the embankment. And so we really need to investigate this. And for that, what I will do very quickly at the end of it, we have carried out analysis for various scenarios. And these are the various scenarios that you see here. And the initial stage and 7 days, if you take 7 days time to build the embankment, or 10 days, or 20, or 30, or you carry out an elastic analysis. So this is the modeler, which is opening one by one, various stages. And then we'll see the results very quickly. And you will see the influence of the time taken to build the embankment. This is done. And so we look at the results. All these options, they will open one by one. And as they're opening, you can also see the factor of safety. So in the initial stage, the factor of safety close to 2, as you can see now, 1.984. And it drops down because of the excess pore water pressure developed. And depending on the number of days taken to build the embankment, the factor of safety is changing. We'll soon see the results in one go. it is done. So you can see that while in the initial stage, the steady state stage, it is 1.984, which is a good factor of safety. But when you build an embankment like this, you just built an embankment in 7 days, the factor of safety is 0.499. And if you do that in 10 days, it improves slightly, 0.608. If you do that in 28 days, it is 0.820, which is the analysis which we carried out. And if you okay, we carried out using Spencer at that time. That is the change. Spencer, that is why we're getting 0.946, if you remember, in that analysis we just finished for 20 days. Let's make it all of them. Yeah, 0.946. If you're doing it in 30 days, then slightly above 1 o'clock, one factor of safety. And if you, instead of choosing advanced material model like Norcent, if you choose elastic or elastoplastic material, which is the last scenario which was done for the 20-day, for which we obtained a factor of safety of 0.946, the factor of safety being obtained now is 1.737, which may be incorrect because of the incorrect, you choosing incorrect material to represent the situation. The actual situation would be this, 0.946, and that brings to the importance of choosing the correct material model. And so let's go back to the presentation. And to sum up, we've looked at the various options and the various options to incorporate pore water pressure and slope stability analysis using Slide 2 are water surfaces, piezometric data, RU coefficient, finite element seepage analysis. We looked at 3 of them: water surface through phreatic surface, piezometric data. We just looked at that. We carried out finite element method seepage analysis for a few examples. And on top of all this, you have the built-in finite element seepage engine to carry out steady state seepage analysis and transient seepage analysis. So with this, we come to the end of this webinar. I'm sorry the time is really taken more time because of so many examples. And the next webinar, and you are all invited, would be the third and the last webinar in this series of webinars on Slide 2. That would be on 1st of July at 3 p.m. Indian Standard Time. And that would be on support and probabilistic slope stability analysis. Now, since I can't see any questions, maybe usually a colleague looks at the questions while one is presenting, but I have nobody at the moment available. So if there are any question, in any case, if there are questions, I would not like to do justice to somebody and not to someone else. Since the time is also up, we can't take all the questions here. So what I suggested that we'll provide an answer by email to all the questions, and keep sending you questions if you have any, and our experts would get back to you with the answers. So ladies and gentlemen, thank you very much for your attention, and looking forward to seeing you on 1st of July at the same time for the third part of the webinar in the webinar series on Slide 2. And as I said, that would be on support and probabilistic slope stability analysis. Thank you very much, and stay healthy, stay safe. Bye-bye for now.